In this lecture, we will be discussing the search strategies in various complex environments, as compared to the previous environments which we discussed, where the search scenario would be or simpler and would be fully observable. So we addressed search algorithms which were fully observable. They were deterministic, static, known environments, with the solution being a sequence of actions. And we will now start to discuss algorithms that search for a goal with path not being very relevant in discrete and continuous cases. And we will expand it also to scenarios where maybe the scenario is dynamic and so on. So what are the strategies for search in case of a less favorable environments? For example, the local search algorithms are algorithms which care about maximizing a certain evaluation function and trying to find how to get from a current state into the next state, which has a higher evaluation function. Maybe we can call it a utility function or objective function. So local search algorithms, they would be operating only on the single current state. They would not keep track of some complex frontier, or let's say a set of already visited states, but they will only operate using a current state and generally only move to neighbors of that state. So by changing just one aspect, that will be a neighbor from one state to another. Like we can, for example, imagine a problem of putting 8 queens on the chessboard such that none of them attack each other. That is a problem to solve, and we know that each queen needs to be in one column, and we will, for each column, we will write down each row in that column the queen is supposed to be. Now, if we do that, then we will have, for example, maybe in the column 1, we will move the queen from one position to another, from one row to another row, and otherwise we will not do any other change. So that will be a neighboring state to the state of which we were previously in. And if that new state will have a higher objective function, we might want to move to that state instead of the original one. It is not very systematic approach, because we might never explore parts of a search space where the optimal solution is, for example. And but on the other side, we use very, very little memory, and it is often we often find reasonable solutions in a large or even infinite state spaces. So, these local search methods are useful for solving optimization problems where the aim is to find the best state according to certain objective function. So the objective function will be the function which we had, like for example, in the A star, the function Fn, which were given as a quality of a certain state. We will have a quality of a certain state given by this objective function. And if we want to, in case of objective function, maximize this value of that function, so find the state which is the maximal of this objective function. But also we can have an identical strategy or analogous strategy where we have, for example, a cost function and we want to minimize the cost. And in case of minimizing the cost, we want to have to minimize that function and not maximize. So we have the state space landscape, which is again, like we had previously the graph of a state space graph. We can also have the state space graph with all possible states laid out on a landscape with a certain locality, certain position in that space, and elevation defined by the objective function or utility function, or with cost or energy. And the aim is to find either a global minimum or a global maximum depending on the formulation and the particular scenario. So the complete local search always finds a goal if one exists. An optimal one always finds a goal in global maximum or minimum. Means that if we have a search strategy which completely searches the state space landscape, then we will find the goal if one exists, and if it is an optimal local search, it even finds a global minimum or maximum, depending on which we are looking for. One such algorithm, which we will be talking about, and it's very important also in the context of machine learning, is the hill climbing search, where we want to maximize the objective function. It keeps the hill climbing search keeps track of the current position and objective function value, and chooses one of its neighbors which have the form the steepest ascent from the current position, so to a direction where the objective function is the highest as compared to our current position. So, and it will go and continue this process until we find a peak, which means that we have reached a point from which no other neighbor will have a higher objective function than the current position. And that means that we have found a peak and we have found the so-called local maximum. This is also sometimes called a greedy local search because it simply just goes and greedily looks for higher objective function until it ends up on the peak. And we can have an analogous formulation for finding minimum, and this is called then the gradient descent method, where the minimum is being searched for. So both of these methods are greedy local searches. However, one needs to be aware of the fact that both this hill climbing search or gradient distance search will lead to the fact that we will get stuck in the so-called local maxima. Imagine the following 1D profile of an objective function. So this objective function for each state has a certain value. This is in our case plotted as a continuum, but it holds exactly in the same way in a discrete case. And we are here at the current state, and we are searching our local neighborhood, and we find out that the neighbor with the highest maximizing the objective function is here. So we will go into this position. And from this position, we will even forget where we came from. And we will again try to find the neighbor with the highest objective function, which will be maybe here. And then we perform one more step, we will end up here, one more step, we will end up here, and here we will be finding us in a situation where all the neighbors have lower value than we have at this position. That means that we have reached the maximum, but it is a local maximum, and actually it is far from this global maximum, which is here. But we will never go to that global maximum because there is a valley here, and our greedy local search for hill climbing will never allow us to go downwards. Additionally, of being stuck in this local maxima for the hill climbing search, and please for the gradient descent and minimization, think of very analogous cases. It's just the exact opposite in a way. We can find also that we have several other structures in our objective functions. For example, we can have plateaus, which are flat area in the state space landscape. And like here, imagine that we are climbing up here. Suddenly we end up in this plateau here, and the question is what to do. So one strategy could be that even if our objective function has the same value, we will still proceed towards the direction of the same value, and in the hope that we are on so-called shoulder location, and after the shoulder the objective function will be again rising. But it doesn't need to be always a shoulder. It can be also a flat local maximum, as we can see here. So all these are evaluation function values which can appear in this search space or in the state space. Now, also, if we have, this is a one-dimensional objective function, normally we have multi-dimensional state space, so a state which is characterized not only with respect to one position, let's say, but many aspects, and we will have 100-dimensional, 1,000-dimensional, million-dimensional state spaces, if you like. And already in two-dimensional case, we have this a situation where we have the so-called ridges. So we have a profile which is in one direction, looking like a local maximum, but in another direction, it can be something which is more like a shoulder. And these ridges are also causing a lot of troubles for the greedy local search to be able to navigate. A hill climbing search from the perspective of the use case or scenario of the position of 8 queens. So for example, we are supposed to put in each column one queen such that the queens are not attacking each other. We can see that this queen is not attacking any other queen. This queen is also not attacking any other queen. This looks very good so far. And when we come here, this queen is in fact attacking this queen. So that's a problem. And the number of attacking queens is therefore, like the pair of queens, is therefore 1 in this case. We can see that for the others, again, the situation is favorable. So this state in state space will be having the objective function, or actually the cost function in this case, because we want to minimize it, will be equal to 0. At the same time, we can say the number of non-attacking queens, and then we could maximize that scenario. So in this case, this is already a very good scenario, and we need to just see whether we can somehow further optimize, find a state in which the number of the pair of attacking queens can be even lowered. So this this can be done by evaluating the for example, all the neighborhoods. So we can see if we change the position of the first queen, or position of the second queen, or position of the third queen, fourth queen, fifth queen, sixth queen, seventh queen, eighth queen. And if one of these changes in this discrete state space, if the change will lead to a better value, meaning the E, the pair number of pairs of queens that attack each other will be 0, then we will find the solution to that problem. With our hill climbing search, or gradient descent search in this case, if we start from randomly generated 8 queen state, meaning like this, for example, that in each column there is one queen, but they are positioned in a random location, we get stuck in local optimum, or local maximum, or local minimum in this case, in 86% of time, and only 14% of problem instances will be solved and find the solution. So that's while this is very little, we are using very little memory for that, and it's just taking on average 4 steps to succeed, to find the solution, and 3 steps on average to get stuck within the local minimum in a state space, which has in total 17 million states, which is quite a lot. So you can see here that this is the current state, and within the state space there are these neighbors, and there are various neighbors associated with, like a neighbor when everything is positioned in the same way, but just this queen is moved to this position, will be associated with the value 15. If we will be, for example, moving this queen to this position, we will have the number of pairs which attack each other lowered to only 12. So that's already quite of an improvement. Or we can choose this position, or we can choose for this column this position, or this, or this, or for this column we can choose this position. Here are again some 12. So these are the minimal values which we would be choosing one of them in one step in order to improve the overall objective function by changing to a neighboring state. So, and with this approach, we will either most likely end up in a local minimum, or in the better case of 14%, we will actually find the solution. And this insight actually brings us to an approach which can be accompanied with the hill climbing search, and can get us out of the local maxima, and that is a random restart hill climbing. So if the hill climbing gets stuck on a local maximum, we simply will try a different initial position, and we will start the local search again. And like in the queens, once we find the local minimum in that particular case, then we will simply just reset it completely, make a completely random choice of the positions of queens with respect to their columns, and try to find the global maximum, minimum with value 0 again. And if we don't succeed and we again get stuck, then we again make a random restart. And this actually makes the hill climbing search, this random restart, makes it complete, because at some point the random restart will actually land on the solution, and we will not even need to perform a local search. And while this might take a long time, at some point this will happen. So with this makes the solution, this makes the algorithm to a complete algorithm. So in general, if hill climbing has a probability of success P, like in our case it was 40% with the queens, we typically would need a reciprocal of P number of restarts in order to find the solution. And generally, the very complex and extremely difficult NP hard problems, meaning those which do not have no polynomial solution, usually have exponential number of local maxima to get stuck on. So with every new input parameter, if you like, we will get an exponentially more of local minima or maxima to get stuck on it. We need to be aware of that. However, we already see that this randomness in the restart is kind of improving our hill climbing method on the theoretical level, and it never goes as the random restart allows the local search to get out of the local or maximum or minimum. However, there could be also a different way how to achieve that, not completely restarting the search process by a completely different initial condition, but to have actually a random walk. So random walk means that we will not walk to the steepest gradient of going upwards in the steepest way, like for the hill climbing, or downward for the gradient descent, but we will make a completely random step in any direction. And this will actually eventually also, random walk will eventually find a solution, but it will be extremely inefficient. So we don't know how long it will take, but it will, on average, it will take very, very long. It will be inefficient, but random walk is complete in itself, while the hill climbing isn't. So the insight here could be that we could combine the hill climbing and its efficiency with a random walk with its completeness to achieve the best of both worlds, both efficiency and completeness. And this relates to an approach which is called simulated annealing, which is the annealing term comes from the metallurgy, where a hardening or hardening is achieved by heating up a certain material, and by slow cooling we allow for this material to reach a low energy crystalline state, and this allows favorable properties for metals or for glass, for example. So this slowing down cooling is used here also in this simulated annealing as a way of combining the random walk with the hill climbing approach. So the simulated annealing combines these two, and it starts with a random walk being dominated in the first phase, while towards the end the random walk will be only very sporadical, and mostly we will be dealing with the hill climbing steps. So as it works, it's the following. We will first pick a random move from a current local position, so to the next neighboring state. And if the new position is better, than the previous one, we keep it. If it's not better, then we will keep it with a probability proportional to the badness of the move. So we had some optimal, maybe the error, the change of the difference of error between our current state and the new state we will be in, whether we will move to the new state is associated with the difference of error. It's proportional to that. Simultaneously, this probability of keeping that move to a worse valued state is the probability is associated with the temperature. The temperature is very high, and it slowly cools off. So this value T is at the beginning is very high, and it slowly goes towards zero. And then the probability can be defined as the E powered by delta E. So if this is very high, then we will most likely not accept that move unless the temperature here is very high, and with that we will achieve a value which is a higher probability. And as we are cooling off, the T will become smaller and smaller, and then the probability of accepting the new state will be then more governed by this value of delta E by the badness of the new objective function or cost function value. Please note that there is this exponential function here is having here this delta E for a badness. The delta will actually be, through the forward differencing, will actually be the, we will have like the negative value here, because the new state will have a smaller value, and the old state will have higher value, and therefore we will have here a negative value of the badness score of the difference of the objective function, and here this will be for sure a positive value, and therefore this will mean that this exponent will be a negative exponent, and therefore the higher the T, the higher the probability that we keep the neighbor with the lower objective function, and the lower the T. If the T approaches 1 or 0, then we will have the situation where this will be most likely rejected, and only those random moves which have better values of objective function will be accepted. In the previous discussion, we have been talking about scenarios where we have only one instance of a state which we are trying to improve by following looking at successors or neighbors of that state with a higher objective function for hill climbing, or lower objective function, cost function for some gradient descent operations. Now, that has been only one instance, and sometimes if we wanted to get out of the local maxima or minima, we were discussing the options of either random restart or simulated annealing, which helped us to tackle the problem of being at the local minimum. However, in case we have more memory available, then we don't only need to have one instance of a state to be changing to a successor state, but we can have several at the same time. So we can have, for example, case states that we are processing in parallel. And at each step, all successors of these case states are generated, and k-best are considered for the next case states. So we maybe do not only create one successor for each state. We can select several successors for each state, and then we choose but only case state. So in some cases, we might get stuck and then we do not follow any further. And in some cases, we have two good options for a successor to go, and we can choose among those states then to be among the winning case states. So in that sense, it is different from random restart, because random restart acts in a sequential manner, where once we get stuck, then we restart. However, in this case, we are running it in parallel, and the states, through the fact that several might have a higher objective function than the others, they communicate and they kind of drag the states which are not, or K runs which are not that successful, to kind of come to the state space part where the objective function is higher. And this, however, might lead to something which is called clustering in a small region. So we will have the, um, the the cluster of the states in one region where there is a high objective function. For some reason, it still does not need to be the global maximum. So this might be undesired. And for that, we can, for example, utilize something like stochastic beam search, which can be implemented in such a way that where we have all the successor states calculated, the case states can be chosen based on the probability distribution P, and this probability distribution P is proportional to the objective function value of each successor K state. So the fact that some state has a high objective function doesn't automatically elevate that state to be one of the K states, but it gives it a high probability. But with this, we still have the randomness, stochasticity, playing a significant role in choosing the K states, which helps us uh, um, to reduce this clustering artifact. So we can see that this local beam search can be actually acting on any of the previously discussed operations, whether it is with simulated annealing or without. But it also has interesting relationship to what we will discuss next, and those are the uh, evolutionary algorithms or genetic algorithms. Evolutionary algorithms are algorithms which are based on the evolutionary theory coming from biology and studies of origin of species. And while this study has been oriented on development of organisms, it can be mapped to um, the evolution of states from states which have little chance to be a good state representing a solution to a states which are scored highly. So we can think of it as similar to somehow to the stochastic beam search in the sense that we are following several states at the same time. We will call it a population in evolutionary algorithms, where the population will consist of many many states, which also could be called individuals, metaphorically speaking, relating to the evolutionary algorithms. And here it is closely related to the stochastic beam search also because several aspects in the stochastic beam search are appearing in some form in the evolutionary algorithms. And there are some additional functional mechanisms in evolutionary algorithms which are act on top of the stochastic beam search. So first off, we have the population of states that is has which is out of the population, there is a small amount of fittest states. So they have the highest objective function value. And in genetic algorithms, these could be chosen to become the so-called parents for the next generation of the states. And as parents, they could act in the form that through a principle called recombination, the fittest states can produce offsprings for the next generation, which will then have also some particular objective function. Often in our genetic or evolutionary algorithms, the states will be somehow represented as a string, as a genetic sequence, for example, from the evolutionary theory, and so that we can perform certain operation on strings, such as trimming and concatenation. And that could be used for the recombination. In the principle of recombination, we could use a varying number of parents that are necessary to produce an offspring. Well, in then typically could be two, which can be seen as two parents for one offspring, as we are accustomed to. We can also have the mixing number could be equal to one. That could be seen as a vegetative reproduction, but we could also have other values of this mixing number that are not observed in nature, but is still possible in the computer. And that could have a perhaps interesting benefits for the algorithm to evolve into states which are more favored than the initial ones. So now we have generated several states. If we have generated several states in this evolutionary algorithm, we will come to the details of how we generate them in a moment. Then we are confronted with the task of selecting the k fittest states. And again, similarly, again to this beam search, we can say that we take the k best. Or the second approach could be like the stochastic beam search, where we assign probability to their selection proportional to the objective function value. So again, we will not have a clear assignment of based on score whether a state qualifies for survival to the next generation or not, but we will have the um, the probability determining the likelihood, how likely it is that it will survive to the next generation or not. The third approach could be that we select random states irrespective of their objective function. Then the recombination procedure, which is unique and not present in the beam search, is based on a so-called crossover point. This is again motivated by the evolutionary algorithms, where we have the crossover point is the point where one gene or one substring of the genetic sequence from one parent is then added and merged with another substring of the genetic information from another parent. So we have then create a new string, which is a result of two trimmed versions of the parent strings. And then we split the parents along the crossover point and combine. And we can combine and generate several combinations of these recombinations. It needs to be pointed out that crossover is useful in situations where the genetic sequence is somehow meaningful, that it's not just a random encoding, but the actual substring has some kind of meaning for the problem we are trying to solve. In such a case, the recombination is meaningful in cases where this is just a random tuple without the neighboring characters having any relationship to each other, then this is not, the recombination doesn't turn out to be any benefit in terms of the search for an optimal solution. It is very useful if the substring represents some semantic components. For example, we can have a substring which is representing a type of arm of a robot, for example, or or another electronic component, and we have another substring which represents another part of a device. And by recombining this substring, we are effectively recombining the actual elements in a more complex system and to try to find out how they work together the best. Then in evolutionary algorithms, we need also a component of randomness, which is similar to those where we have the randomness integrated in the hill climbing, for example. In this case, we will be talking about the so-called mutation rate or mutation itself. Mutation in biology means that in a genetic sequence, a, um, a um, uh, uh, some genetic character is maybe wrongly read, or it's wrongly positioned. So there is a wrong character at a certain position, which is an error in the process on one hand, but on the other hand, it allows the evolution to explore unexplored areas and perhaps find better um, states. So this is also adopted into the evolutionary algorithms where we have the mutations, and these mutations can be occurring on the offsprings, meaning that we can randomly change something in that sequence of string or numbers which they represent, and this mutation will then maybe perhaps bring a better objective function. So this randomness is integrated. It needs to be um, considered how much of this mutation do we want to have in the in our uh, consideration. For example, how often should it occur on the offspring? Out of maybe 20 um, characters, should be just one mutated or with a certain likelihood, or 10. So that is the mutation rate. And also, if we have the mutation, maybe we want to have a mutation which is a little bit similar to the simulated annealing, in the sense that we first have a stronger likelihood of mutations in the initial um, um, stages of the local search, and then we are somehow cooling down the population in the way that we allow for less and less mutations over the generations. So this is how we can control the randomness in the evolutionary algorithms. Then the question is, if we have the next generation, what is its makeup? So one idea could be that we have only the offsprings. So they need to be created by the recombination of the parents. But some evolutionary algorithms admit the fittest parents to pass on into the next generation. So that could be something like an elite of parents. The most healthy parents survive longer, and they will be members of the next generation. And that will also secure that the objective function on average is kept high. So all these are aspects of evolutionary algorithms, and we will now have a look at those in the context of the eight queen problem, where these evolutionary algorithms can be nicely showcased. So in the eight queen problem, we have eight queens, which each of the queens needs to be placed in one column on the chessboard in such a way that the solution is found when none of the queens attack each other. And we have different states, and these states can be described in the following way for the evolutionary algorithms. We can have a sequence of numbers, like, for example, we can see here, where we have 2, 4, 7, 4, 8, 5, 5, 2, and this is telling us where the particular queens are located. So in the column 1, it will be in the position 2, in the column uh, uh, in the next column 2, it will be in the position 4. So this looks like we are describing this particular situation here. And then we have 7. No, this is not here. 7 would be here. And then we have 4, 8, um, and so on. So no, sorry, 7 is here. And then we will have 4, because this green here, or this green chessboard, and this green chessboard were previously together. We will come to that. So when this green or blue chessboard is one parent, which is this parent, and we can see how this encoding now defines the position on the chessboard. This describes the states. The second one is the 3275241, and that looks like this is 327 and then 4 5, this is 4. Um, so um, so this is not the same, obviously, but these mm, uh, we will see how this recombination will generate these states. So if we look at these particular cases, 2, 4, 7, 4, 8, 5, 5, 2, we can see that they are describing us some scenario, and this scenario can be awarded with some objective function. And this objective function can be describing the number of non-attacking queens as opposed to attacking queens. The ideal case is the solution is 28, where there is no queen attacking another queen from its respective column. So if we now look at the first case, we will find out that the overall score of the objective function is 24, meaning that the uh, uh, the number of non-attacking queens is quite high, but it's not the solution. To clarify, that this number is number of pairs of non-attacking queens. So if we will be looking here, we have the pair of non-attacking. This is one pair, this is another 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 pair of non-attacking queens. However, this one is attacking queens doesn't count. That's why, that's how if no queen is attacking the other one, then we will have actually 8 times 7 divided by 2 non-attacking pairs of queens, which will be the solution. So in this case, we have only the number is 24 of number of pairs of non-attacking queens, and this is clearly the highest. This is 23, which is slightly lower, but still very good. This sequence encodes positions on the chessboard where 20 is the score of the value of the objective function, and the last one has 11. We can also assign here a certain probability, and this probability will be associated with the chance of choosing this parent as the for the recombination, and or choosing the parent for surviving to the next generation. So now we can see that here we see that there is a recombination. These two parents have been selected for the recombination based on their probability, and the recombination crossover point has been defined after the first 3 columns. So does the recombination make sense for the evolutionary algorithms? One can say yes, because in evolutionary algorithms, we have, in queens, we have a relationship between the neighboring queens in the sense of whether they are attacking themselves or not. So it has a meaning to define substrings of the chessboard description. So that's what we have therefore done here. We have defined the crossover point, and we can see that the parent number 1 now and the parent number 2, which have been then selected for the recombination, are now recombined, where the first substring is from the first parent, the second substring comes from the second parent, and vice versa. So we generate two offsprings from these parents, and these are the new states. And we can see how these two states then look like. So we see here that this state and this state is now forming us a new state where we can see that this part is here and this part is forming this another state. And that represents basically this 3, 2, 7, 4, 8, and then 5, 2. And it's not that we will be detecting that this is a problem, which it obviously is, the position of this queen, but we have randomly decided for a mutation, and the mutation of this at this position leads to the fact that this queen is repositioned to the position 1. And in that sense, it will also, in fact, reduce the amount of attacking queens, which will lead to a better solution. So we can see that in this particular case, the mutation was, in fact, beneficial. The second child is also, or offspring is generated by the recombination. And then we have the two other parents. So this this is a parent which is a parent for two different offsprings with a different parent. So we can see here that there is a now substring. The crossover point is somewhere else, and we have generated the two new offsprings. And again, these offsprings, they were subject of some random mutation. And this way we have generated the new generation of offsprings, which we can again put in at the beginning of our optimization process, or the process of finding um, uh, maximal potential states with a maximal potential objective function, and perform again the same operations of evaluating the fitness, recombination, and mutation. This is how the approach of evolutionary algorithms can be applied to the 8-queen example, but it also can be applied to many other examples where we have a discretized state, and it can be characterized by some string, especially when the substrings have a particular semantic meaning, and we can define the crossover points on these along these substrings. Now we will switch the gears and we will be talking about the local search in continuous spaces. So far, we have discussed the situation of local search in discretized spaces, although we not always have related to it as such, but all the previous discussion was about a discretized space. Now, here we are, if we turn to a real-world problems, the environments in real-world problems are continuous. And that means that, for example, there are infinitely many states we can reach from a current state as their local neighbors. So it's just that we can go in any direction of our state space, and there we can find another state. Then, the branching factor as such has not really a good meaning in the case of continuous spaces. So therefore, previous techniques, most of them would have a hard time to handle continuous spaces, and we would need to develop some new methodologies. So we will be discussing this on the example of building 3 airports in Romania, so that the sum of squared straight line distances to the nearest airport for each city is minimized. So once again, we are building 3 airports in Romania, and we want that they are placed in a good position, that each airport is is serving well a part of a Romanian city, and therefore it's a suitable piece of infrastructure. So the sum of squared straight line distances would be a heuristic of representing the real distance to the airport, but this is for simplified or relaxed problems an adequate um, um, uh, requirement. Then the we need to point out that there is that it's not that we want to have that each airport is well achievable from each city, but from the nearest set of cities. So each airport will somehow be associated with a cluster of cities for which that airport is the closest one. And we want to minimize this sum of all the squared line distances. So let's have a look again at the map of Romania, where we can see the various cities placed here. Here's again Bucharest and all the others. And we can see that we can place maybe one airport here, one airport here, one airport here, and that would probably be serving the infrastructure of the country reasonably well. I have placed this one on the line. However, it doesn't need to be on the line, but it would be natural if the airport will be somehow near the actual road infrastructure. We can define the state space by 3 coordinates, two-dimensional coordinates of these airports. So for each airport on the 2D map, we have a coordinate for X and Y. So for the first airport, we have X1, Y1. That would be one airport, like maybe here, this would be X1, Y1. Then we will have X2, Y2, another airport, maybe here, and X3, Y3 will be maybe here. And these are the parameters of our input parameters of our uh, or parameters to optimize of our problem. And we need to find out these parameters. Therefore, our objective function is a function of a vector x in general, we can call it, which is the vector x is the tuple of these 6 coordinates, x and y coordinates, but now generalized as x. So, the objective function is calculated in the following way. So we can see here the formula, the formalism of the requirement we have formulated in the previous slide, where we have the squared straight distance from A to the airport from any city. So here we have a sum over three different airports. So and this is the this is so this is the position of an airport xi, and this xc is a position of a city. So and here this is the squared distance. So if we will have a square root, this will be forming us a straight line distance, the Euclidean distance, but without the square root is a squared straight distance. And then we are performing the sum over all cities C in the cluster CI. So the cluster CI are the cities which are nearest to the airport I, to the, let's say, first airport first. Then once we finish that sum over that entire cluster, then we calculate the sum over the another cluster, and then we calculate the sum for the third cluster, and that will be forming us the objective function. And now, if we will be moving the CI somehow, this will slightly be changing the, first of all, the distances from to the cities. But at some point, if the change of the position is too significant, we will also have a change in the cluster set, because suddenly an airport will be becoming nearer, maybe closer to one city which it was before not close to, and therefore that city will somehow join its cluster. So and this is an continuous space, because the x and y for each airport are continuous variables. They go on the real axis, and their values are like, let's say, um, continuous GPS coordinates, if you like. Now, how do we solve this this problem of finding the three airports? Well, one approach could be turning it to a set of approaches we are already familiar with. That could be that we will, instead of just dealing with the continuous space, we will be dealing with a discretized space or discrete space. And we first will discretize it in the space into the finite number of states. We can create certain positions on a grid with some spacing delta, at which the airports can be placed, and we will evaluate their overall function, objective function there. And we can use the local search approaches in order to find the maxima. Then each state, in this case, will have 12 successors, because we can vary the each state coordinate by plus minus delta increments, and that will mean that each such increment will constitute one neighbor of our state in our discretized space. So we will have 12 successors, and we can measure, for example, what is the objective function value of each of these 12 successors, or we can use some other measure, which could be, for example, just randomly choosing few successors and measuring their objective function, and then assigning a probability to which state are we moving the next. And in principle, any of the discrete search algorithms will work on this problem. Alternatively, we can sample a fixed amount of successor states. We said that we have, in continuous case, we have infinite number of successors, so we can simply sample the neighborhood of our parameter space, of our state space, and choose a limited number of successors and evaluate what is their objective function. If we perform the difference to the current objective function from the state we are currently positioned in, that is we will basically create a difference in the gradient, difference in the objective function, which will basically define as the gradient of the objective function based on samples, and that is called the so-called empirical gradient. Then, in such a case, we will move in random directions by some increment delta. We will measure the change in the value, like in the discrete version of the steepest ascent hill climbing, and then we will be using this change based to the probability of choosing the next step in this continuous space. Then we can also include the delta being of different sizes over time. So we can have initially larger increments of that the delta is jumping further away in an initial parts of the algorithm, and towards the later stages, or we will then reduce the delta so that it is not changing its position very dramatically, and hopefully it got close to a local maximum, and it is then climbing on that one at that point, analogous to the situation we had in simulated annealing. However, we do not only have the machinery of an empirical gradient to calculate where we want to move next with our within our continuous state space. We can also use the actual gradient calculated analytically. Our objective function, which we were discussing before, has been the sum of squares of the individual coordinates for each airport in the case of the 3 airports case. And this objective function can be simply it's a function, and if we perform derivative of that function, we can obtain the gradient. So as this is a multivariate function, meaning that it has several input values, it has a vector as an input, a vector of these 6 coordinates, 3 times 2-dimensional coordinates of these airports. We can calculate the gradient of the function, and this gradient is can be used for defining us various interesting properties. So first of all, you might remember from calculus that 0 in first order derivative indicates that we have reached a certain position in a function that is actually an extreme value. Another extreme value, we either know the maximum, the minimum, or some kind of inflection point where the function is changing from a positive gradient to or positive value of the first order derivative to negative one. Doesn't need to be extrema in this case, but often the extrema are characterized by the minimum and maximum. It's important to say in that those positions, the second order derivatives in these positions are non-zero, while the inflection point second order derivatives are zero. Now we have the minimum and maximum is therefore characterized by the gradient value. If we have a gradient which is a zero vector, then we are with our position corresponding to that gradient where it was calculated at, that will correspond to a position of a zero of a minimum or maximum. And even if we are not on the extremal positions, the gradient gives us direction and magnitude of a steepest slope. So in case of an uphill um, um, ascent in our state space, continuous state space, we want to use the gradient value to tell us which direction to go next. We can see here that the gradient of a function, this characterized as a nabla of f, is the gradient of has components which are the partial derivatives of the function with respect to these variables or these input coordinates, if you like. So we need to so it's a vector. And if this vector will be zero, then we are on an extreme. If it's not zero, then it points us towards the direction of the steepest slope. Now, how do we calculate these individual coordinates? So that is simply as a partial derivative, which I think you had on your previous classes, where you can calculate for a, let's say, xi coordinate here, you can calculate the the um, the partial derivative with respect to xi coordinate as taking that xi coordinate as the varying variable and the rest of the input variables as constants. And as they are constants, they will be falling out from the entire sum, and we will end up in, for each coordinate, having essentially this kind of partial derivative. So it's 2 times the difference between the cities and in the cluster with respect to the corresponding airport coordinate, which we will be having here as the partial derivative. And that will give us the gradient value, and we can calculate the steepest ascent then by simply the new position, and this x is bold, meaning that it's the entire set of the coordinates x1, y1, x2, y2, x3, y3, and we are calculating it from the old coordinates plus the gradient of the function times some alpha, which will be determining us a step size, how far we can go. And it's also called in machine learning the learning rate. This is a central equation in the optimization process, where the optimization is in every machine learning machinery the key component. So this gradient here is simply added with a small portion to the current position, and we get to the new state. If alpha is too small, the learning rate is too small, the step size is too small, then we need many steps to get to a good position, let's say the global or the maximum position. If the steps are too large, we can overshoot the maximum. And one approach how we can deal with this would be that the alpha can be dynamically changing. So we start with larger alpha and we are again cooling off and having smaller and smaller lambda with each calculation of the new state in our local search. So this approach goes very deep into the architecture or the internal parts of the machine learning machinery. And we will here just give it a very lightweight introduction as we are doing now. And you will revisit this on more advanced courses within your studies. So we have now a formula how we can go into the new state, but somehow we can also think of how can we get the value of uh, the gradient to become zero. So we search basically for a maximum value, and the maximum value can be found by searching for where the gradient of this function is a zero vector. And for that, we can utilize machinery from numerical methods to find the x position which corresponds to the zero gradient vector. So imagine now I'm calling the zero gradient, the vector, the gradient vector as a function of gx. And for a simplicity, I'm just having a single variate case here. So the gradient function is just equal to zero. You can think of it maybe as just this one partial derivative, which we had explained will be this one single variate function. And then we can utilize the so-called Newton-Raphson method for finding the root of a function. So this is now a function. It is a gradient function or first order derivative function, and we are looking for a zero because our aim is to find the maxima and minima. But for the Newton-Raphson method, it doesn't really matter what we are trying to achieve here. It simply is a method which finds the roots of a function. Root of a function is a position on the function where the function is equal to zero. So this is exactly what we want. Now, very shortly, I will devise here the Newton-Raphson method where we will be first expressing a slope for which will be a kind of approximation of a function with in two positions. We have first the position xy on the function and position x1, y1 on the function. And with this, we can create a kind of a slope. So these are two-dimensional points on the function, and we can find out what is the slope of this function, and the slope is this value m. In fact, this value m will be the tangent of a certain angle, but that's maybe not that important. What is important is that this basically describes us is a description of a line, and the parametric description of a line based on 2 points and their slope. Now we can use this formula here in such a way that we relate this y here being the y here, but the y1 will be the function of, so it's like the y is g function, so it's the value of y will be found by the g, and 1 will be the x current. And then we have this m is in fact the first order derivative. This is the slope, and at certain position, if we have in a limit, this slope will be the tangent. So it will create us this first order derivative. And then we will have this x minus x1. So x is x new and x1 is x current. So we have here now the formulation of the Newton-Raphson method, except that this y, we know what we want to have it. We want to have it being equal to 0. And as it is equal to 0, so this we can reformulate such that we have this x new is equal to x current minus g divided by the first order derivative of the g. And in the multivariate case, which we will be dealing with, it is the x new is equal to x current. So these are all the coordinates. And then we do not have this first order derivative or the reciprocal of it, but we have the second order derivative because this function itself is already the first order derivative. It's the nabla, and therefore here we have the first order derivative of the first order derivative, so the second order derivative, and that in fact is not a gradient but the so-called Hessian matrix. So the function which we originally had was a scalar. It's a multivariate function with multiple inputs and a single output value, but its derivative is then a vector. So it's a multivariate input and it has a vector output. And then this Hessian matrix is having a multivariate input, and it has it is a matrix or a two tensor, as you would be calling it in machine learning. And in our case, this matrix is a 6 by 6 variables, and each element of this matrix is basically describing as the second order derivative of this function with respect to two coordinates, either the same coordinates or different coordinates. And what we can see here is that the HI measures how much does the slope in the direction xi change when you move in the xj direction. So we have a slope, that's the first order derivative, in the direction xi, that's the first order derivative, and its partial derivative in that sense, the component of the gradient. And then we change the position by moving into the xj direction. We are measuring how does that slope change then. So this is a first order derivative of the first order derivative, and that is the value which we are storing in each location. From the equation of the gradient components, which we have seen, we see that each of diagonal values are equal to 0 because it's only the one xi component there, and so if it's the second order derivative with respect to xj component where the I is not equal to j, then it's not appearing in the first order equation. So no matter how you change it, there is no change. So the change will be 0. And in the diagonal value, it just equals twice the number of cities in the cluster CI. So therefore, we are just measuring the number of cities times 2. It will be the second order derivative, and those values will be on the diagonal. Now, in our calculation, we therefore have this matrix vector multiplication, but it turns out that it's an inverse. The Hessian matrix will be an inverse. That means that this vector is the diagonal values are reciprocal, and also what it causes is just a multiplication of the diagonal terms with the actual vector, and which generates us another vector, therefore, and this result is therefore then just a scaling of the individual components of the gradient vector, and eventually this will lead to a um, so be added to the or subtracted in the case of this Newton-Raphson method from the previous x coordinate, and we will be searching. That will give us the value of the of the uh, of the position where we have our gradient is equal to 0. So with this, we have calculated the gradient at the gradient value, and the gradient 0 will determine us the maxima of this objective function, which we have specified for this particular problem. However, as the continuous case is not immune to getting stuck in local optima. So that means that we will again find some local optimum, and we might not never reach the global one. So in fact, if you think about it, if we have a certain initial location of our airports, these airports will then be moved. They will be associated initially with certain nearest cities. They will form a cluster. And within this cluster, we will simply, they will try this finding the local search or the optimization process will move our individual cities into the locations of these as a centroids of these clusters, and the centroids of these clusters will become the local. Well, I was calling it a local maxima, but actually it will be the local minima, because we are trying to minimize the distance between the overall distance between the cities and the airports. As in the previous cases, we can use local restarts or simulated annealing in order to get us out of this state of being stuck in the local optima. And this is the end of the lecture on searching in complex environments, and especially local search in both discrete and continuous cases. And next, we will be looking at the constraint satisfaction problems, where we are expressing a certain problem by a set of constraints, and we have a systematic approach how to find a solution given the constraints which we are given as the input specification.